sorry to interrupt.
No, that's okay. Good catch. I would have. Okay, so now it should be. Does it look like it's recording?
It does.
It is? Okay, cool. We'll cut that part from the beginning of the video. I was being confused.
Okay.
Okay, so that'll be the first part of the talk. And then the second part will be optimizing control schemes for superconducting qubits in the context of circuit quantum electrodynamics. So we'll talk about one control scheme called DRAG, D-R-A-G, stands for derivative removal with adiabatic gates. And so I'll talk about sort of how this was developed in the first experimental implementation of DRAG. I will point out there are many other control schemes. I don't have time to talk about all of them today. So this is just one of them. Okay, so before we start, does anyone have any questions about what we'll be talking about, or should I just dive right in? Okay, let's go ahead and get started then. Okay, so I should move this. Okay, this will have to be good. Okay, so as experimental physicists,
On the side, just the single square. The single square?
there we go. That's good.
Why
Perfect. I don't know, that's where it went. Okay. So as physicists, something we know and love and understand quite well is the harmonic oscillator, both classically and quantum mechanically. So here we'll just sort of look at the easiest quantum mechanical circuit we can make, which is the harmonic oscillator, and we'll learn some cool things about it, and importantly, why it can't be used as a qubit or two-level system or many-level system. So the way I would draw this as an electrical circuit is shown off to the left here, where I have some classical voltage drive, and then it's coupled to an LC circuit. And this capacitive coupling just means that it's not connected with a wire. It's well, there's a capacitance between the drive line and the resonator. And we can write down the quantum mechanical Hamiltonian, which describes this system as seen in the middle of the slide here. So we have equally spaced energy levels, and the transition energy or transition frequency between each of the levels is given by 1 over the square root of LC. And this is actually the same result you would recover as if you approach the problem classically. So this is a nice sort of classical to quantum description here. But in the quantum case, we get this extra 1/2 here, which represents the 0-point energy of the harmonic oscillator. Now, if we plot the potential in red off to the right side of the slide here, we have the 0-point energy, and then each transition indexed by h bar omega 0. So this is just our ladder of equally spaced energies from the Hamiltonian. And this can't actually be operated as a qubit because if I apply a classical drive to the system, we enter what's called the correspondence limit. So the excitations just keep climbing the ladder, and all of our expectation values quickly approach what you get from a classical system. And so that's not very quantum mechanical. That will make a good quantum bit. But this example does teach us something about how to take a classical circuit, quantize it, and then learn things about its energy levels. So this is a really nice sort of first example. And these harmonic oscillators are actually what we'll use to couple to our qubits. So although it doesn't make a good qubit, it's still essential in the operation of a functional qubit. So in the bottom left-hand part of the slide here, and I probably should have made this a little bigger, is two sort of pictures of what these harmonic oscillators look like in practice. And actually the simplest way you can make one of these is you go to the machine shop and you ask them to make a metal box with a rectangle carved out of it. And then you know from solving Maxwell's equations that there will be normal modes of the electric field in that box, and we'll use one of those modes to couple to our qubit. So that's what figure A is here, just a slot milled out of a metal box. And then there's also many types of geometries you can use here. So this is this one in the right is something called a stub resonator, where the electric field comes out of this stub, and we can use that to couple to our qubit as well. Okay. All right. So from the first part, we talked about why harmonic oscillators aren't good qubits, because we enter this correspondence limit with equally spaced energy levels. And so to isolate any two transitions in the system, we need to introduce some anharmonicity, something that makes our energy levels not equally spaced. And the way we do that in practice, specifically in superconducting qubits, is by replacing the inductor in the LC oscillator with a Josephson junction. And so what a Josephson junction is two superconductors separated by a thin, not superconducting layer. So here I've called it I for insulator, but in principle, it could be magnetic. It could be just something as long as it's not a superconductor. And in superconductors, the charge carriers are two electrons which pair up together and form something called a Cooper pair. And in a Josephson junction, these Cooper pairs can tunnel from one side of the superconductor through the insulator to the other in a coherent process. And so this is, there's many fields of physics specifically dedicated to Josephson junctions. So I won't have time to go into all of that today, but really cool systems. And we can use the Josephson relations, which are the constituent equations for Josephson junctions, to write down what the inductance of one of these structures is. And we see it's not a linear inductor. So that means that Lj for Josephson junction, does not depend linearly on I. Okay, so this is, when we plug it into a circuit, we often draw it as an X rather than a squiggle for an inductor. And its inductance is given by this equation here. So here I0 is what's called the critical current, and I is the current flowing through the junction. Okay, because it's a quantum mechanical object, we can write down a Hamiltonian for it, and we get these two terms. So this first term here represents the charge imbalance due to an unequal charge distribution across the Josephson junction. N hat represents the difference in Cooper pairs across the junction. And this parameter Ng represents the total external electrostatic environment at the junction. So this is sort of accounts for things like fluctuating charges in the background. It could represent a voltage bias to the system, everything like that. We just combine it into this one parameter. Okay, and then this last term here is called the Josephson energy, and it depends on cosine phi, where phi is the phase difference of the superconducting order parameter across the junction. So question for the audience, just to make sure you're still here a little bit at least. If I Taylor expand this cosine phi for small phi, the first order Hamiltonian will look like what? From the first slide. So the first series will be phi squared, right? And then so I would have n squared plus phi squared. And if I impose a certain commutation relation on n and phi, this would reduce to a harmonic oscillator. And then the second term in the Taylor series would be like phi to the fourth, and this would be the anharmonic part, which makes the Josephson junction have these unequally spaced energy levels. Okay, so this cosine here is really the special thing that lets us allow this as a two-level system.
I have a question.
Yep.
How hard is it to measure N sub G?
Ooh,
Is it important to?
good question. In 2 slides, ask the same question, because I was going to say something about that. Yeah, this is great. And the good thing is we can control EC and EJ in fabrication. So by FEM design and careful design of the circuits, EJ and EC are totally obtainable by us in something like clean room, and we can make these circuits with very high precision. Okay, so now hopefully we've motivated why we'd like to use Josephson junctions to create our two-level systems. And we can actually plot what the energy spectrum looks like as a function of this parameter Ng that represents the electrostatic environment. And we see, so I should point out here, this black line represents the ground state, the blue line is the first excited state, red is second excited state, and then at the top green is just the next level. And we see that, and this is solved, I should point out, for EJ over EC equals 1. So the charging energy and the Josephson energy are the same here, but we'll see later we can change them. And we see, depending on the value of Ng, the energy difference between the ground state and the first excited state can change by quite a bit. And so this is a problem for qubits, because if you have this fluctuating background of charges, that can dramatically shift your qubit frequency, and that's equivalent to a phase error. And so small changes in the electrostatic environment can be huge issues it's the issue for the first generation of superconducting qubits, because the fluctuating background charges led to huge dephasing. And so to answer your question, Jacob, in this regime of superconducting qubits, knowing and controlling NG is very important. Because if I have, an electron in the substrate, which is moving around far away from the qubit, it will dephase the qubit. And I don't really have any hope at controlling that electron. So the question is, we can fabricate the device such that the transition frequency between black and blue is about 4 to 8 gigahertz, which corresponds, when you convert to a temperature, to about 500 millikelvin. And so by placing these things in commercially available dilution refrigerators, we can cool the system to its quantum ground state. And then so just by passive cooling, we initialize the system to this black energy band. And from there, we can hope to use it as a 2-level system. Okay, so this charge noise is quite frustrating. So in 2007, there was a really nice paper, which is referenced here, and I'd highly encourage you to check this out if this is something you're interested in. And what this paper discusses is, how can we get away from this charge noise? And so as we make the ratio EJ over EC larger, these bands seem to flatten out. And so for sufficiently large values of EJ over EC, specifically about 50, it doesn't have to be exactly 50, we get these energy bands which are perfectly flat as a function of offset charge. And so if I fabricated my device to have this ratio of EJ over EC, now knowing NG is not important at all, because my qubit transition frequency is the same, no matter what's going on in the offset with the offset charge. And so this is often what's called the transmon regime. Transmon stands for transmission line and plasmon oscillation, which isn't important here, but it's kind of a weird name. That's how it got it. And interestingly, sometimes you'll see experiments where people purposely design this EJ over EC to be lower than the transmon regime. And then they operate the qubit as a sensor for the fluctuating electrical environment. So sometimes is bad for dephasing. Sometimes it's kind of interesting to learn about for fundamental physics. Okay. But of course, nothing comes for free. So the transmon's great, protecting from charge noise, but what are the downsides? Well, if we look at this first graph of the EJ over EC is approximately 1, we see that specifically, let's take 0 offset charge, for example, the energy difference from the ground state to the first excited state is very large relative to the transition from 1 to 2. And so that difference in energy is what we call the anharmonicity. And for low values of EJ over EC, it's quite easy to make large anharmonicities. For the transmon, we see, although the energy bands are flat, the anharmonicity is quite small, meaning that the difference in energy to go from the black line to the blue line is very similar to the difference in energy from the blue line to the red line. And so the potential issue here is that by addressing the 0 to 1 transition, it's possible to accidentally address the 1 to 2 transition, or the blue to red transition. And now, rather than operating your system as a qubit or 2-level system, you're operating it as a Q-trit, a 3-level system, or you could even address higher energy levels. And then all this nice quantum information theory we know sort of falls apart, right? We don't have 2-level systems anymore. We now have n-level systems, and that makes things much harder. Okay, does anyone have any questions at this point? In the chat? No?
I think you're good in the chat. And
Right.
is it a problem that the first and second excited state are almost degenerate, or is that not really a thing?
The first and second excited.
Sorry, in the case of the ratio equaling 1, so the
Oh, yeah.
the leftmost case. You already mentioned this isn't a great regime for qubits.
Yeah.
It's so sensitive.
Mhm.
But,
Oh, the fact that the blue and the red are so close to each other?
yeah,
Is that an issue?
also a problem in addition, or is that the only thing with that?
Let's see. So yeah, it potentially could be an issue if you're, well, let's see. So you'd have to think about which transitions are allowed in the system, right? If you can go from 0 excitations to 2 excitations, if that's an allowed transition, that could be an issue.
Okay.
But if you can only go from 0 to 1, then you're protected by probably exponentially by that.
Gotcha. Okay.
But that's it. I've actually never thought about that. I might need to read it more. Yeah. So okay. So the transmon's great, but we can have this issue, which is often called leakage. Okay. So yeah, here's a nice sort of picture of. So this dashed line represents the phi squared potential. So this is a harmonic oscillator. And then the blue line represents the cosine potential, which is introduced by the Josephson junction. And then again, we've just plotted the horizontal lines as the energy levels. And it turns out that the alpha, the anharmonicity, is just equal to the capacitive charging energy. So in fabrication, this is also a parameter we can control, but we're always fighting this trade-off between charge sensitivity and lower anharmonicity. Okay, so so we've talked about the harmonic oscillator a little bit, and we've talked a little more in depth about the Josephson junction, which constitutes the qubit. Now, how do we combine these things and have a functional qubit that we can manipulate and measure its state? And in quantum optics, this is described by something called the Jaynes-Cummings Hamiltonian. So it consists of three terms. The first term represents the qubit as a two-level system. So this level, the Jaynes-Cummings Hamiltonian, just assumes that we can isolate these two transitions to make a real two-level system. The second term represents the harmonic oscillator. And the third term represents the interaction between the two systems. So we have this coupling rate G, and it represents these two processes. Let me make sure I get the order right here. So this first one represents the qubit losing an excitation and the cavity gaining an excitation. And the second term represents sort of the exact opposite of that, the qubit gaining an excitation and the cavity losing an excitation. So we just have these two systems and they trade excitations at a rate G is the way I typically think of it. And what this actually looks like in practice, we have two pictures here. So this figure A represents a 2D geometry. So this is everything's fabricated on one plane. And the harmonic oscillator here is described by this coplanar resonator here, and the corresponding electric field profile given by this, what would you say, salmon line, pink line, the pink line. And the Josephson junction is represented by this green, kind of looks like an H here. And it's fabricated at a certain point in the transmission line such that the electric field antinode couples to the dipole moment of the qubit. And so the interaction would look something like the electric field dotted with the dipole moment. And it turns out that leads exactly to this interaction term in the Hamiltonian. You can also do this with a 3D resonator. So here's the resonator I had on the first slide, and then the qubit is fabricated and kind of slotted into the cavity like this, where the electric field is still parallel to the dipole moment of the qubit. Okay, so you can set this up in many ways. Here's two. I think these are nice pictures which describe what's going on. Okay, so the next step that we often do is we take our Jaynes-Cummings Hamiltonian and we operate it in what's called the dispersive regime. And what that means is G, the interaction strength, divided by delta, where delta is the difference in frequency between the cavity and the qubit, is the ratio G over delta is very small. And so that allows us to do perturbation theory on the small parameter G over delta. And the resulting Hamiltonian looks like what we have here in this middle line. So again, we have our qubit and our cavity. And now sigma Z and the mean photon number in the cavity are coupled like this, where this G squared over delta is often called the dispersive shift. So now what we often do is regroup terms in a sort of suggestive way, where we group all the A dagger A's together, and it looks like the effective frequency of the cavity depends on sigma Z, which represents the excitation number in the qubit. So what that looks like in a measurement or in a Python notebook. Yeah, sorry.
Can we go back one slide?
Yes.
So in figure 8.
Yeah.
So this is that superconducting circuit that was like represented on the previous slide.
Let me check the previous slide. Yeah, so the Josephson junction is, well, it's obviously, not to scale, but is this little sort of dot-like looking thing in the middle of these two long green pads.
Okay.
And then these pads are form the capacitance between the center pin and ground of the circuit. So the size of these pads dictates EC, or the capacitive charging energy.
Okay.
And then EJ is determined by well, you can't see it here, but basically by the overlap of the Josephson junction. So like, what's the overlap of the two superconductors separated by an insulating barrier? So EJ is not very easy to see here, but EC is essentially dictated by the size of these capacitor pads. And then, yeah, what we do is attach wires to each of these pins and measure the cavity that way. Any other questions about the devices? No? Okay, cool. Here, okay. So, right, so the effective cavity frequency depends on the state of the qubit. And so what that looks like in measurement or in some sort of simulation is The cavity is represented by this red Lorentzian curve. And when the qubit changes states, the expectation value of sigma z would change from -1 to +1, and the cavity resonance would shift by 2 g squared over delta. So often we call it g squared over delta chi. So that causes the resonant frequency of the cavity to shift, or if we measure the phase of the cavity, that would represent a dip in the phase. Okay, so the way we actually measure the state of the qubit is by measuring what resonant frequency the cavity lives at. If it's at, in this picture, if it's at the red dot, the qubit might live in the ground state. If it's at the blue dot, the qubit might live in the excited state. All right. And this allows us to do conditional drives on the cavity, meaning if the qubits, so this would be in some sort of logic loop. If the qubit's in ground state, do this drive. If the qubit's in its excited state, do something else.
Do you to measure then the resonant frequency of the cavity?
Yeah.
Do you drive the cavity through a bunch of different frequencies until you
Exactly.
until measure upon the output?
Yeah. So what we do is, so imagine this pin is like the cavity input, and this pin is the cavity output. What we do is send in energy at a certain frequency at this pin and measure energy out at this pin at the same frequency. And then you'd sweep through these frequencies. And the resonant frequency of the cavity is when the transferred energy through the circuit is maximum.
Gotcha.
And so this would be like it even says here, transmission amplitude. So the peak in the transmission amplitude is what we call the cavity frequency or the cavity resonance. Right. And so we can also regroup the dispersive James-Cummings Hamiltonian in another way, where the effective qubit frequency depends on the mean photon number in the cavity. Sorry, I've been thinking about phonons a lot lately. And this causes the qubit absorption spectra to be split by individual numbers, each peak corresponding to a different photon number in the cavity. And so this data here is actually real data from our lab, taken at some point during the last couple of years. And so each dip represents the absorption spectrum of a superconducting qubit, and each peak represents a different distribution of photon numbers in the cavity that it's coupled to. So you see here on average, we have maybe 1 or 1.5 photons in the cavity. And so this is as fundamental physics, I think, is really cool, because this allows us to measure, first of all, the distribution of photon numbers in an electromagnetic cavity, which again is just this metal box that someone cut a hole out of, right? And we can count individual photons in that box, which is pretty awesome. And it also allows us to learn about the statistics and the fluctuations of these photons. And from a quantum computing perspective, it allows us to do conditional operations on the qubit where the condition is the number of photons in the cavity. So we could drive each one of these peaks independently. Okay, so using this toolkit on the previous slide and on this slide, we can conditionally drive the qubit, conditionally drive the cavity, dependent on things like their coupling to each other and their relative losses and things like that. And this allows us to do prepare and measure non-classical states of light in superconducting qubits. So these are simulations. I did not take this data, but what this might allow us to do is prepare a quantum state in the cavity with exactly 3 photons and measure its quantum mechanical analog of a probability distribution. So this is something called the Wigner function, and it represents, like I said, the quantum mechanical analog of a probability distribution. And really interestingly, it has negative values. So classical probability distributions don't have negative values, right? They're all positive, but in quantum mechanics, your probabilities always go like amplitude squared. And so the Wigner function can take negative values, which really is a sign that like, hey, this is a quantum mechanical thing. And these sorts of things have been prepared and measured using superconducting qubits. And it also allows us to create these really cool things called photonic cat states, which are superpositions of photonic coherent states. You might ask, why are they called cat states? And it's because this quantum interference between these two red blobs looks just like cat whiskers, or so whoever named them thought.
But also the Schrodinger's cat thing, right?
Yeah, so Johannes and I debate which one it is all the time. I'm pretty sure it's because of the whiskers. Yeah, so I know this is sort of out of left field, but really what I wanted to point out here is that these coupled quantum systems not only allow us to operate the Josephson junction as a quantum two-level system, but also allows us to investigate the fundamental quantum properties of light, or whatever sort of degrees of freedom you're coupled to. Okay, so here I'll take a little question break if anyone has any, and then we'll transition to the second part of the talk, if there are no questions.
So you said like to measure energy levels of qubits, you have to this frequency sweep.
So that frequency sweep measures the resonant frequency of the cavity, and where that resonant frequency is positioned can tell us about the state of the qubit.
Okay.
Yeah.
So I've been told often that quantum computing systems are very delicate, and
Yes.
you kind of have to have like no input of energy for them to function.
Right.
So how does that kind of exist alongside? We need to like.
Right. So
astronomical frequencies to-
yeah. So you see in this figure here, we're sending in. So you populate the cavity to a very low excitation number, and so then you can think of the cavity having, for example, a single excitation, and so that excitation can be traded back and forth with the qubit. That's great. If I send in 10 million excitations, it's going to sort of drown out all the quantum properties of the system.
Okay.
And so we need, it's very important. So we spend a lot of time calibrating how much power we're sending into the system, because if you send in too much, everything becomes like a classical system. And so it is a very delicate calibration process to do this. Yeah, that's a great question. Any other questions?
I think, is it true that the cat states have been used at like Yale as like the qubit states?
Yeah.
And if that is true, is the reason for that, I mean, it's because coherent states are nice, so why not just add only two of them together and then?
Yeah, so the reason cat states are quite popular is because if my quantum state is a photonic state, the dominant loss mechanism for a photonic state is single photon loss. And coherent states are eigenstates of the photon lowering operator, right? And so that allows us to essentially measure if we've lost a single photon without destroying the state. And so because of that, they're really promising candidates for things like error correction, where the error syndrome is just like measuring if I have an even or odd number of photons. And then if that parity has changed, I know an error has occurred. Mod the loss of 2 photons, which is exponentially suppressed relative to a single photon. Yeah. All right. So now we'll transition to talking about, well, what's the best way to apply these energetic pulses to the system? So here on the left, I have a picture of Google's famous Sycamore chip. And so you can see all these lines on there. I think there's something like 52 qubits on this chip. Many of the qubits are coupled to multiple readout resonators. The qubits are coupled to each other. There's going to be independent lines to adjust the electrostatic environment. It's quite complicated. There's a lot of things here. And as an experimental physicist, someone hands me this chip. They hand me a board that looks kind of like this. So this board is able to shape pulses I send into the system. It can time these pulses. It can relate the amplitude of one pulse to another. And our job is to create something that looks like this, which is sort of an optimized quantum circuit that we could put into something like QuIC or your favorite quantum simulator. And we want the results, which are experimentally produced on the left, to more or less match the results produced by our simulator on the right. And as you can see, this is quite a hard problem, right? There's a lot of moving pieces, and they're all coupled to each other. And well, it's a hard job, which is why quantum computing hasn't been solved yet. And so what we'll be talking about today is minimizing this leakage in transmon circuits. And if we're able to do that with something like this board, which allows us to shape our pulses. So that's what I'll be talking about for the remainder of the talk. Okay, so like I said earlier, the relative anharmonicity of the transmon is small. And by small, I mean anywhere from 5 to 10%. So the anharmonicity is approximately 5% of the transition frequency. And what about leakage? So if I apply a pulse at this arrow to move from the ground state to the first excited state, how do I know this isn't going to happen and make my system into a quote unquote QDIT consisting of many levels? And how can another question is, how can I figure out whether or not that happens in the first place? And then a follow-up is, how do I minimize it? So first, we want to consider what our voltage pulses coming out of the arbitrary waveform generator actually look like. So it's not an instantaneous thing. We need to apply a voltage at a specific frequency, mainly the qubit frequency, and its properties will shape the transition between the ground and excited state. So that in time might look something like this, where our voltage is this sine wave where the oscillation frequency is at the qubit frequency, and the envelope is maybe something like a Gaussian envelope. So this orange line here is just the envelope, and blue is the actual voltage going into the system. And we have all these parameters we can mess with. We have T0, which is the center of the Gaussian part. We have the frequency, we have the phase, we have the width of the Gaussian pulse. And it turns out that just by controlling these parameters, we can minimize the state leakage. So the way we determine, what's actually being driven is by looking at something like the Fourier transform of the voltage pulse in time. And here I've plotted just the Fourier transform of a Gaussian, which is also just a Gaussian. These are actually generated with the exact same function in Python, and that's what we got. And so it's actually the spectral components of the drive are distributed in frequency. So it's not just at a single frequency, and the width of this. And so it should be centered at the qubit frequency. But what could cause leakage is if we have some significant component of the drive spectrum existing at omega 1, 2, which would populate me to the second level. And now we have this leakage problem. And again, the detuning between these two we'll call delta. So I guess sort of a question for you guys and talk to people around you is, how can I minimize the width of this pulse? Or the first question I would ask is, what dictates the width of this pulse? So let's take, 10 seconds and think about it, and and see if we can come up with what causes it. Because the wider this is, the more leakage I should have, right? If I could make it a delta function, I wouldn't have a problem.
Oh, yeah.
I'll go back to this slide if it helps. Okay, so does anyone have any thoughts, any guesses? What dictates the width of this spectrum? I think I heard two people say it. Yeah, someone over there. Yeah. So yeah, the width of the Gaussian envelope, right? And so the way I think of this is, if we have an infinite width Gaussian envelope, then that's just a sine wave, right? And if I take the Fourier transform of a sine wave, I get exactly a delta function because there's only one frequency component. But the more narrow I make this, the wider my spectral distribution will get. Okay, so this has an easy solution, right? We make all of our pulses infinitely long. Okay. Yeah.
So if your pulse is too long,
Yeah.
probably will suffer from decoding.
Exactly. Yep. So we're fighting this battle of, okay, we need a sufficiently long pulse so that our spectral distribution is narrow and we're not driving transitions. But the pulse also needs to be short enough so that our physical quantum system isn't decohering during the pulse. And so it's a sort of before we introduce any optimal control schemes, we're fighting this balance between these two things, which is hard. Exactly. So the width is set by inverse of TG. So TG is the gate time. And if my gate time is very long, 1 over a big number is small. So I have a delta function frequency. I always have to do it that way. Okay, so we know that this actually just it won't work to minimize state leakage because we're fighting this battle between decoherence and leakage. So our goal here is to optimize essentially to optimize the shape of the pulses so that we can cancel out these other spectral components. And then we can maintain short drive pulses so we're not losing against decoherence. We just need to think a little bit harder about the way we shape our pulses. Okay.
Basically, what we want to do is create a specific shape for the pulses in order to have desired Fourier
Yes.
spectrum
Yep.
of this.
Yeah. And there'll be a picture in 4 or 5 slides maybe. And it looks maybe a little different than you'd expect.
So like in theory, you could get around this by like filtering your signal, filter out the frequency components, but then would that just be unrealistic? Like if you
So-
move frequencies, then you're gonna also have to like.
Right.
figure out a bunch of components in the signal.
So for a short pulse, I'll have quite a wide spectrum, right? But I know I need to have the component at omega 0,1 because that's what's going to give energy to the qubit. But I know at 5 or a little lower in frequency, I also have omega 1,2. And so realistically filtering out omega 1,2 distinct from omega 0,1 with something like an inline filter is very hard because they live so close together in frequency, and certainly wouldn't work in like a general measurement setup because you can't have like a continuous filter, right? It always has an edge. But yeah, if you could perfectly filter everything out before it went into the system, that would also do it.
So regarding your comments on how you use a zero mode machine, and they actually can do some filtering on the machine.
Well, that's not.
So QD test back in zero mode. They actually did some filtering.
And this would work only if you have the fixed.
Yeah, if you fit, yeah, and then as you slide it, you'll have to. I mean, if you could custom design like a notch filter or something with a continuous notch, it might work, but I don't actually know how you do that.
So, and the trade-off still exists, right? Theoretically, right? So if you filter to make smaller frequencies, it doesn't necessarily increase your.
Oh, so I think Cameron meant generate the short pulses, except that you'll have this bad
okay.
spectrum, and then put something like a physical filter in line before it gets into the system, so that it filters out all this bad stuff.
Oh, okay.
Yeah.
Oh, okay. Like noise, like.
Yeah.
high frequency Noise, okay. I
Yeah.
see.
But physically implementing that might be a little tricky. But to be honest, it's not something I've spent a lot of time thinking about. Okay, so this particular part might get a little math heavy, but I'm also hoping to outline some key principles in quantum optics, which are sort of globally useful, not just to this problem. So the way we'll consider our system is by a 3-level system here. In principle, you could consider more systems, but for now, we're just worried about leakage into this second excited state. So my Hamiltonian, which describes the driven system, is given by omega j, pi j. So omega j indexes the frequency of each transition, and pi j is sort of like the generalized sigma z operator. So it represents the operator which drives the transitions. And then this second part in here represents a classical drive applied to the system. So I have some time envelope. Lambda j represents the coupling to each transition. So in principle, you could couple to each transition with different strengths. And then this term, which creates and destroys excitations in the qubit. Okay, and in principle, the time envelope can be broken down into this component here. So ext cosine omega d and then eyt sine omega d represents that we can perform independent x and y rotations of the qubit. So this, in this case, cosine omega d would represent x rotations of the qubit, and sine omega d is just 90 degrees out of phase and represents y rotations to the qubit. So this is sort of the, yeah.
What's J here?
So J indexes the transmon level. So it, sorry, yeah, so this, sorry, it should start at 0, but it should be 0, 1, 2. So, yeah, so it's, yeah, it should start at 0. So we have 3 transmon levels, level 0, level 1, and level 2. Well, no, it should start at, yeah, because there's only 2 transitions, so it should start at 1.
Transition, but 3 levels.
Right, so omega 1 represents the transition between the ground state and the first excited state,
Yes.
and omega 2 represents 2 and 3. So it should start at 1.
Okay.
Yeah, and lambda J is the coupling of the drive to each individual transition.
So
Yeah. So if you had lambda 2 equals 0, you would not couple to the second transition with the drive at least. Okay, and so yeah, and so we can shape each quadrature of the drive independently, so we can do independent rotations about X and Y. Okay, so here we'll introduce a couple sort of math tricks to simplify this Hamiltonian a little further. But it actually makes the Hamiltonian much more complicated, but it makes it into something we can actually manipulate and optimize. So the first simplification will transform the Hamiltonian to a frame rotating with the drive. So we'll use the unitary operator uj to rotate each transition at the frequency omega d. And the Hamiltonian transforms via this, this transformation here, which is a common tool in quantum optics. And you might see many places, but I wanted to at least have it here so everyone could see it. And the second assumption we'll make is we'll neglect any terms that oscillate very quickly. So if we have any terms like e to the I omega 1 plus omega 2 times t, we'll assume as we average over time, they oscillate fast enough that their average is 0. Okay, so any terms that look like this, we just sort of throw away. And this is called the rotating wave approximation, if you've heard of it. Okay, and so when we apply this transformation, our Hamiltonian looks like this, and I apologize, it extends onto the second line. And so here we've introduced these 2 detuning parameters. So the detuning of the drive between the first transition and the relative detuning of the drive with the second transition. And again, now we see more clearly at the Hamiltonian level that this EX envelope of time corresponds exactly to sigma X. And likewise for EY corresponds to sigma Y. And our transition frequencies just get reduced to these deltas. Okay, everyone happy with this? Maybe still not super clear how we can optimize anything, but this is a valid transformation. Okay, so we'll do it one more time. This transformation, so now V is another unitary. And to be quite honest with you, I can't motivate why it has this form. This is just taken from one of the papers. It has this form, and the Hamiltonian rotated again has this form here. So we'll just go through term by term. We can talk about which ones are good, which ones are bad. So this first term is a rotation about X between the 0 and 1 levels. This is totally fine. It's actually something we need to be able to address the 2-level system as a 2-level system. This second term here represents a rotation between about the effective x-axis between the ground state and the second excited state, which is at quite high energy. And in principle, we shouldn't be sending any energy at that frequency into the system. Even with this, even with quite a broad spectral distribution, this one should not be driven. So we'll just ignore it and not worry about it. This term here represents an effective shift of the frequency of the second transition, which we're hoping to minimize anyways, so we won't worry about it. If we destroy all coupling to this term anyways, it shouldn't. The fact that its frequency moves a little bit isn't a big deal. This term here represents an effective shift to the frequency of the first transition, which we would like to minimize because we don't want this frequency to be moving around all the time, because that'll cause dephasing errors in the qubit, just like charge fluctuations would. So we would like this to be 0 if we could. And this term here is the really important one. So you see it is responsible for driving transitions between the first and second excited states. And so the magic of this technique is we can pick the parameters of the drive exactly such that this coefficient cancels out, and then this coupling is just gone. Okay. Yes.
Should I think about these changes in structure?
Yes. Yep. It's just a star shift. Okay, so any other questions about this slide? I know this is quite a lot of information, but I didn't want to.
There was two lambdas to start, right? What is the lambda without, wasn't there two?
Oh, yes. So they're picked to be defined in terms of one another. So lambda 1 equals something lambda 2, I think,
Okay.
something like that. So they're rescaled to one effective lambda.
Okay.
I forget exactly what that scaling is. It's in the paper somewhere. Okay, so here's our Hamiltonian again, and we'll pick the drive parameters to be shaped like this. So this term cancels the unwanted drive to the third level, and then by picking delta 1 to be equal to this, we'll minimize dephasing errors to the qubit. Okay, so now, okay, I was sort of running out of time. I thought I would have less time at this point. So the experimental results are quite quick. So we'll go over them sort of one at a time. So Nias, to answer your question earlier, this is what the pulses actually look like with this pulse shaping. So we have our normal Gaussian shaped pulse EX, and then EY is related to the derivative of EX, which is exactly what we have here. And then beta just accounts for this negative and the scaling. So EX is Gaussian and EY is derivative of Gaussian scaled by something. And so I'll describe these measurements first based on measurements from the Yale group around 2010, I think. So the top panel here is using regular Gaussian pulse shaping. And so the black shaded in lines are what you'd expect from sort of a perfect system. And the lines with the slashes through them represent simulations of the composite system with these poorly shaped pulses. So it's like a 3-level system that you're coupling to the unwanted 3rd level. And then the solid lines are the measurement results. So I would say, based on looking at this, and then the x-axis here denotes certain gate operations on a 2-qubit processor. So I would say that the master equation matches the measured values quite well, but those are quite distinct from what the perfect system should see. And so this is because of short pulses driving to the 3rd level, and you don't recover a 2-level system because you don't have a 2-level system. You actually have a 3-level system. Okay, this bottom panel is by using this drag pulse shaping. So by using this pulse shaping scheme, they measure almost perfect matching with the theory for a 2-level system. So they've really concluded here that they've canceled out any excitation into this 3-level subspace just by shaping the Y quadrature of their pulse. Yep.
Do you by chance know what the is for their
I don't remember, but I don't remember exactly, but if I generally remember, I think the qubit frequency is about 5 gigahertz and anharmonicity is 300 megahertz or so. So the percent would be 300 megahertz divided by 5 gigahertz, which is 6%. So consistent with transmons, but I'll have to double check the exact numbers here. Okay, so yeah, this pulse shaping really gets rid of single qubit gate errors, which is great. And by measuring the fidelity of gate operations as a function of the number of gates applied, using these 2 different pulse shaping techniques, the top panel represents the Gaussian shaped pulses. And so this dash line at 0.5 represents a perfectly mixed state. So the quantum information is totally lost. And they measure after about 20 pulses, we've totally decohered our qubit by just totally coupling to the 3rd level very strongly. Using drag, the pulse shaping scheme we talked about, we see at 20 pulses, maybe only a 20% loss of information, something like that. And it takes almost 100 pulses to totally decohere the qubit. So very quickly. Yeah. Yep.
So here beta, how did they find the beta from? Have they found it by optimizing it, like
Yeah.
repeating experiments at different beta, or they did some spectroscopy measurement first, extracted the positions of the levels and the frequency, and then from that data you can estimate what beta is supposed to be.
I think
Just iteratively go
so I think beta is found via an optimization process.
Just optimization.
Yeah. I would have to double check, but I'm pretty sure it's found that way. Okay, so what they've done is simulated the system. So extracting the error per gate as a function of drive length. So remember the short drive lengths are what's really bad for these not pulse shaped systems. And they see that the measured error per gate almost exactly matches a 3-level simulation. And so what this means is that at short gate or gate times, your 2-level system is actually totally a 3-level system. It's totally described by a 3-level system, which is a huge problem because all of our theories talk about 2-level systems, and we've designed this operate as a 2-level system. However, if you do this derivative pulse shaping, it matches exactly a 2-level system. So we're really just totally throwing out this extra level simply by not changing any of the circuit parameters except for the shape of the drive pulses. And really, you're only changing the shape of one of the envelopes, which is pretty cool. One of them you just get to do with, as you always do. And then, so the same sort of not optimization, but measurement of fidelities is calibrated using a set of 2 qubit gates, and similar result is found where the drag is about 10 times more efficient at preparing known quantums or desired quantum states versus the Gaussian pulse shaping. Okay, so that's actually everything I have for today. Yeah, that's it. So if there's any questions, I'd be happy to take them. If not, thank you for coming. And
Any questions for Joe? With that
Oh.
hand, that's it. Yeah. So I guess this was a talk, or at least partially about optimal control. So it's clear to me that this derivative pulse shaping is much better than
yes,
Gaussian.
it's about a factor of 10, depending on what metric you use.
Yeah.
But yeah.
But I'm curious, the mathematical part of me is it optimal? So with respect to some
Yeah, right.
goal, right?
Yeah. So I'll say no. I know there are many pulse shaping techniques which are used to further optimize this. This was just the first one. And so I would have to refer you to the video in the email today. There's a really nice talk about sort of the history of this, but I didn't have time to learn all of them for today, just the one. So
What type of approximation to start with Hamiltonian? And then, as Joe said, let's use 3 levels.
3 levels, yeah.
Let's use all these. Let's use rotating wave approximation. And what can we do from these kind of considerations of this approximation? If probably you a little bit weaken your approximations, start to include other parts like equilibrium rules and other schemes should be applied.
Yeah.
Cool. Yeah. And I'm curious if, given all these approximations, though, if Joe's scheme you presented
So he showed
is the best one.
Yeah.
Oh.
If you go back a little bit to his slides, I think that's the best you can do here.
Yeah. Right, because this sum only goes over 2 transitions. And so if you add a third one, do you get any other couplings which go like lambda squared or something?
I see.
And I'm not sure there, but it'd be good. Something interesting to learn about for sure.
Other questions? If not, let's thank Joe. one more time.
Is there anything in the chat I can see?
No, I've been checking. Nothing else.
Okay, cool. Thanks, guys.
Cool. We'll have a career o'clock.